And so today the topic again is going to be shared memory communications using direct memory access relative to System Z13, GA2, and Z13S. And so on this next chart you'll see we have the agenda. And what you can see, the agenda is logically divided to 6 topics. And the first 3 topics are really overview and background information. Topic 1 is actually a review. Whereas topics 4, 5, and 6 get into the how-tos and how to use it. So again, on the agenda you'll see what the topics are. We're going to have a review of SMC-R because you'll see that this is just a variation of SMC. And then we'll talk about the new variation, SMC Direct. And then we'll also talk about the new hardware that makes this capability possible in System Z. It's ISM, Internal Shared Memory. And then on topic 4 we'll talk a little bit about how to use the function, how to get started, the requirements, and a little bit about IP connectivity relative to SMC, and then a little bit about testing, verification in terms of how do I know it's being used, and then we'll also remind you about the SMC applicability tool, how you can evaluate your benefits or potential benefits for SMC in general. So the SMC applicability tool again applies to SMC-R and SMC-D as well. And so if we move on to the next chart, this next few charts then is a review of SMC-R, and recall that SMC-R is based on RDMA technology. And chart 4 here you'll see that RDMA is about accessing host memory directly over a fabric without using the CPU of the remote host. And what you'll see here is that in this case RDMA is provided by different technologies. And in this case you would need to exploit it, you would need an RDMA capable NIC and an RDMA capable fabric, and then of course we'd need a protocol to exploit that technology. And so SMC-R was about using RDMA for providing communications, and the fabric also needs to be a lossless fabric, and so Rocky makes this capable. And if you look at the next chart, on chart 5, you'll see that we made this capable by providing this protocol called shared memory communications, and it is sockets based. And so applications are not required to change. It's a way of exposing a memory block to a remote host, and we can perform communications by sharing memory with the remote host and doing that over a Rocky fabric. And so IBM introduced the Rocky Express adapter on the EC12 and now a Z13, along with the software protocol of SMC-R for remote access into another platform. You can use that technology for same CAC or cross CAC, for ZOS to ZOS communications for SMC-R itself. And it was intended for cross-platform. And you'll see at the bottom, as a reminder, we published an RFC to make this available to the industry. And so we're hoping that we'll have other exploiters in the future. For now, it's a System Z ZOS solution only. So again, this is SMC-R as a reminder using Rocky. And then on the next chart, and so this is a very important concept. You'll see to remember that you use SMC-R by rendezvousing and connecting and managing your connectivity by using TCP/IP, using your existing TCP/IP IP topology. So we find each other using TCP. It's very similar to the concepts of SSL in terms of you connect using TCP/IP fabric. You can negotiate and exchange your credentials, and if both hosts are capable and enabled, then in fact we can switch out dynamically and use SMC-R and the Rocky technology to transfer user data. And that connection, the TCP connection, controls who you can connect to. So that connection will stay active and idle for the life of the connection. If the TCP/IP connection were to terminate for any reason, we would also drop the SMC-R connection. So again, it preserves all of your qualities of services for in terms of who you can connect to, how you can connect. And then at the same time, we use the Rocky adapter for exchanging data, but preserving the TCP connection. And the fabric is basically looked at as one fabric. So here you'll see the old technology is depicted in green, which is basically Ethernet. And then on top of that, we'll superimpose an RDMA fabric, which is in fact the same physical fabric. We just exchange Rocky packets or frames, which all that work is done by the adapter. And also you'll notice that conceptually that the Rocky and the OSA adapter are logically sitting side by side and associated with each other because we have defined them to have access to the same physical network, and we tie those or associate those two adapters by an identifier called a PNet ID So on that physical port that attaches to that green cloud, which is your physical switch, or to that yellow cloud, which is just frames on top of that fabric, they're associated by having the same PNet ID. And so we're going to use that concept again here when we talk about SMC-R. But again, this was targeting cross-CEC communications and a more optimal, less latency, higher latency in terms of normal fabric versus reduced latency with Rocky, and a better CPU footprint as well. And so again, to connect with SMC-R, you start by connecting with TCP/IP. And then on to the next chart. And then a reminder of what was the benefit of SMC-R, what's it all about. And so here is our original performance charts that we've made available through several different publications. But basically the way you read this chart, again, this is about under each metric or each benchmark, you'll see there's 4 bars. And blue is the throughput, and the green and yellow are CPU, both on the client server. And then response time is in the purple. Hopefully you can see those colors. And what you see as you go from left to right, essentially all we're changing is the benchmark number of connections will be 10 request response. The first one is RR1 connection, and then we use 10 connections going from left to right. And from moving left to right, we just increase the payload size. So you'll see how the characteristics of the performance, you'll basically see it increase somewhere around RR10 2K, 4K. And then as we move to the right and we start exchanging larger messages, you'll see that what happens is the CPU benefits increase. Where over on the left-hand side, it's more about throughput and response time. Over on the right-hand side, it's both latency and CPU savings as we move to the right. And so you'll see the benefits actually are quite nice as you get out into like 8K. You'll see these are 4 or 5x times the throughput. And again, the comparison here is SMC-R protocol using Rocky compared to TCP/IP using OSA 10 gigabit. And out on the right, as those blue bars sink down for throughput, you'll note that we've saturated the bandwidth, and so the opportunity for exceeding a 10 gigabit OSA basically drops down as we move right to larger messaging. So you'll see that for SMC-R, again compared to TCP/IP over standard Ethernet, the opportunity for savings is significant using that protocol. And again, when we talk about response time, it's measured at the application layer where it's API to API. That's one round trip. That's considered response time at the application's view. But there's no business logic or middleware involved. It's just exercising the socket API and the networking technology and comparing technology A to technology B. And so that, again, this has been available for 2 or 3 years now. This is SMC-R using Rocky. And then on to the next chart. And so what was that all about? So what's the value of using something like SMC-R? Well, first and foremost, it's about performance. You're either interested in CPU savings, latency, response time, or all the above. And it's leveraging a new technology using RDMA. And SMC-R does that. And the key to that is transparent to application software. So no software changes in your application. It's based on TCP sockets. And it leverages an existing Ethernet infrastructure. So again, in theory, there's no changes to your LAN fabric. It does require 10 gigabit Ethernet, but essentially it's still Ethernet. We do not require any special switches other than 10 gig for your Rocky Express adapter. And it preserves your existing network security model. So anything that you have in place, anything from SSL to IP filters or VLANs, anything you do to isolate or preserve network security, that is not disturbed by SMC-R. In terms of resiliency, the protocol does provide dynamic failover from one adapter to another, so we do not disrupt workloads. And then in this architecture is also transparent to load balancers. We know for enterprise data centers that's important because there's several solutions that use TCP connection level load balancers, something like Sysplex Distributor, and again this solution is compatible with that. And then finally, it preserves your existing IP topology. So you do not need to provision different IP networks or IP addresses. As long as both hosts have access to the same IP subnet, they're eligible to use SMC-R. So your network administration model in terms of managing your Rocky fabric is virtually identical to what you do today in terms of managing an IP network. So that was a review of SMC-R, and hopefully most of that you're familiar with and you've heard of, and maybe you heard a few things new, but it should be something that most of our customers are familiar with by now. So if you could flip to the next chart, please. And so we'll go into SMC-D, and what is that about? What's the difference with that versus SMC-R. And so in this topic, this will be new information. Everything you've heard up to this point was review. So, this next chart, we'll talk about SMC-D itself. So now, the protocol itself, shared memory communications, what would it look like using that inside the machine from LPAR to LPAR, or guest to guest, or ZOS instance to ZOS instance, and why would we just not use RoCE or OSA, or what would be the advantages of applying this protocol to a different model? And so what we show here is SMC Direct over ISM extends all the value points that we just discussed with shared memory communications architecture by enabling it for direct access from LPAR to LPAR without using a hardware adapter or hardware bus, etc. So basically, you provide all those qualities of services as you had with SMC-R, but now directly from within the machine. So again, you do not require network adapters or consume PCI bandwidth or ports or I/O slots in your machine. Network resources like switches are not required. So basically, you get the benefits of SMC without the requirements for hardware. And so really that's the objectives of what SMC over SMC-D is about. So as we go to the next chart, what you'll see is that we'll fill in some of the blanks here. So once again, we leverage SMC protocol, and instead of using RoCE adapters, we'll use this new technology on Z13 called internal shared memory. And you'll see here that it's described as a CHID. In some of these screens, I'll have it as a VCHID, which is it's virtual in the sense that it's a logical adapter, but it will be defined as a PCI adapter. We'll talk about that more in a moment. But what you'll see is that each host now has a function ID, PCI adapter access to it, and they will use the shared memory protocol directly, well, again, without going across a device interface. And what this does logically, or the concepts here, is it really tightly couples the API communications to the memory within the CPC. So you can just view this as, again, similar to HiperSockets in the sense that we directly access the memory of the other host, but here now it's done on a socket basis, leveraging these shared memory communications protocols. So we don't packetize our data or use the device architecture like we do with HiperSockets. And so really what that does then, again, SMC eliminates the TCP/IP processing in the data path, but again, you use TCP/IP to connect and manage your connectivity, but it is not used for data communications. Now, ISM itself is provided by system firmware only, so there's no additional hardware. If you have Z13 GA2 level or Z13S, you have the technology. And so this is basically a high-level view of what SMC Direct looks like. On to the next chart, please. And now you'll see, okay, so here's the big picture view of what it looks like if you combine the solutions. And we're going to look at this. So you'll note on this chart that there's a reference to another chart, chart 35. When we get there, it's just another view. It's kind of a view of the IP topology of the view you're seeing here. And what you have is combining RoCE and SMC-R and SMC-D together. And the protocols do work together, and they dynamically determine which form I can use. So the host that's in the middle here, ZOSMH2, can use both RoCE or ISM, and it will determine when it's talking to image 1, it will use ISM. It will determine that both are on the same footprint, and then when it rendezvous with host image 3, it will determine that we're not on the same footprint, but we are eligible for SMC-R. So the appropriate form of SMC is dynamically chosen based on proximity, and so basically you can leverage both solutions simultaneously, RoCE for going across the floor, ISM for same machine, and you get the benefits of SMC in both environments. And so you would compare this three-tiered solution. What I'm showing here is WAS on the left, DB2 in the middle, and WAS on the right. As an example, you could compare that if all three connections or both connections were TCP/IP using either HiperSockets or OSA versus, again, what we can provide with SMC Direct or SMC-R. You can imagine the performance benefits if you could apply them on both tiers. And so if we move on to the next chart, you'll see a little bit about let's talk about the performance and value of it. So why is this really any different? I understand I can avoid the hardware for going across the floor, but how does it perform? And so again, what we'll see here is we're going to compare this to HiperSockets. And as you know, HiperSockets provides significant performance because it is also memory to memory, but it uses TCP/IP and it uses a device model. The architecture is based on QDIO, Whereas in this model, it's a different architecture. It's PCI based, and it uses SMC for communications. And so what you'll see there is a significant difference. In some aspects, it's an apples and oranges comparison. In some cases, the comparison is relevant. But nevertheless, you'll see the performance benefits are usually expressed as latency, throughput, CPU cost, and of course scalability. How do you virtualize it? How many users can use this thing? And you'll see in each case here there are significant attributes for each of those characteristics. And so for workloads for ZOS images that have significant amount of communication, this is where you get your benefit. How do I find those workloads and where do I know I can benefit from this? We'll talk about the SMC applicability tool at the end. But again, if you have workloads that are intensive in terms of communications and you have the opportunity to co-locate them, this technology can benefit you significantly. And we'll look at the performance benefits now. So if you flip to the next chart, please. You'll see here now again the scale and the intent here is the same as we looked at for SMC-R. But what we're comparing here now is TCP/IP using HiperSockets, LPAR to LPAR if you will, versus SMC using ISM. So it's SMC-D versus TCP/IP. And again, once again, moving left to right, you'll see the same thing. A little bit different in this case. On the far right, we actually have streaming workloads. But moving up to there, we still have request-response workloads. The 4 bars still mean the same thing. You know, the green and yellow is your CPU savings compared to HiperSockets, your throughput relative to HiperSockets, and the response time. So, as you know, again, this is what's considered a micro benchmark with no application business logic. And for the same benchmarks that we always publish, you'll see here, moving left to right as the data moves larger, it's still 10 connections for this request response pattern. You'll see that once again the CPU savings goes up, and again relative to HiperSocket, you'll see all the data patterns on the left-hand side are around a 60 to 70 to 100% improvement. And as you move in the data in the middle, where you get a little bit larger data messages, you'll start seeing 3, 4, 5 times the throughput, along with 60, 70% CPU savings. And then finally on the right, if you look at a couple of streaming workloads, where the first one is 1 connection and the next one is stream 3, let's just look at memory-to-memory bandwidth and what it looks like comparing, again, HiperSockets to SMC-D. Now you see some pretty interesting numbers where the fact they're almost unbelievable when it's 700 or 800 times the throughput, and you'll see the response time is right at 90% faster in terms of round-trip time, and the CPU savings in both the client and the server in this case is right at the high 80s or 90% in terms of the opportunity to save for CPU versus, again, HiperSockets. So that's a pretty interesting set of numbers. Again, the bar was already fairly high with HiperSockets, and so now this technology leaps over that bar by quite a bit. And so you'll see that in some cases it's 9 times the throughput comparing the two technology. Again, this is SMC-D using ISM compared to TCP/IP using HiperSockets. So going to the next chart, this is just a summary in words of what you just saw in bar graphs. But the summary is also pretty interesting. It's a little bit different perspective. It breaks it up into 3 summaries, whereas the top is request response patterns, that's small data. And then the middle is request response patterns, but large data. And finally on the bottom, it's a streaming workload. And once again, we list the 3 attributes that you typically describe for performance, which is latency, throughput, and CPU savings. And so you can see for each type of classifying your workloads, you'll see there is significant opportunity for savings for each one of those. And finally, you'll see that for larger data, you see bigger savings in CPU and throughput, where again it's 6, 7 times the throughput. Streaming is up to 9 times, with a 90% reduction in response time and CPU cost itself, again compared to HiperSockets. So very interesting performance metrics that we have comparing the two technologies. And now to the next chart, some customers that do not use HiperSockets for one reason or another, they might want to know, well, I have same-cat communications, but primarily it's through OSA. And so how would this technology compare to using OSA? And this is what this chart shows you. And now you start seeing the gap is even much more significant. And so again, all the benchmarks are the same, moving left to right. We start with 1 connection and we move up to 10. We change the message size, moving left to right, and you'll see now the opportunity for throughput is very, very high. So There, once again, in the middle, you're talking about things like 16, 14, 15 times the throughput, 90% savings in response time, with CPU savings are, again, very high. Finally, moving to streaming, you'll see comparing, again, TCP/IP over two OSAs that are running through a switch. This is an external OSA going from one LPAR to another versus a workload that is going directly from LPAR to LPAR using SMC-D over internal shared memory. You'll see the comparison is somewhat apples to oranges, but the fact is its communications started with TCP/IP, switched out to SMC, and you'll see the difference in opportunity in terms of the performance metrics is quite compelling. So when you have 21 times the throughput in some cases for the Stream 3, which is, so now this is just memory bandwidth of based on the architecture of SMC-D and ISM. So again, compared to OSA, so if you look at the next chart, we provide the words behind the charts, and you'll see that, again, at the very top, it's request response small payloads, and you'll see request response large payloads, and then finally streaming, again, providing a summary of latency, throughput, and CPU cost. And so the numbers are quite compelling, where you're talking 20 times the throughputs, 14 times. Again, the CPU savings opportunity is also significant itself. So now what we added on this chart was finally a real workload in the sense that it was FTP. So look at how does the streaming really translate to something that's real. So in most of you know, for FTP, we cannot change the throughput. The networking is essentially waiting on the DAS-DIO processing. So what we can do is provide the efficiency improvements for networking, but the bandwidth itself is not going to change because basically the bottleneck is I/O. But what you'll see here with using, again, comparing FTP transfer against an OSA versus SMC-D, you'll see again a CPU savings opportunity of 58% on the receiver side, and a 26% savings on the sender side using SMC-D as opposed to an OSA connection. So again, very compelling numbers for FTP, how it translates in terms of opportunity for savings. And then on to the next chart. Now here is just kind of a high-level view of the value of what SMC-D is. So a little bit about SMC architecture, an introduction of SMC-D. Again, in concepts it's similar to HiperSockets with the fact that you can communicate in the box and the data is not exposed to an external network. And the client use cases are really multi-tiered or co-located workloads. Again, it's improving that co-location value point on System Z. And it's, again, the main point is there's no application changes. We'll talk about how you enable it. In TCP/IP, there's one parameter that turns the function on. You can also use the applicability tool to assess your traffic to find out if it makes sense for you. If you're already using HiperSockets, you already know you have the justification. If you're not using HiperSockets, I would encourage you to reevaluate why you're not and look at this technology. And then off the right, you'll see some of those same highlights that we described in the previous charts. And then moving to the next chart, you'll see another one. This one just tries to put SMC-D and R side by side and emphasizing the value of remote communications across platform and internal communications using SMC direct. And you'll see again, it just calls out some of the attributes along with the CPU savings, FTP in this case, we use that example. And it's just again a little bit about the two technologies as you combine them together. And then on to the next chart. So finally we wrap it up with what is the SMC value of SMC-D. And so starting at the top, it's really about optimization. It's about making co-located workloads on System Z very competitive in terms of providing more value for workloads that sit on the same platform. So it is. It's about optimized communication first and foremost. But the first bullet or check mark there is really everything we just described or reviewed for SMC-R applies here. So whatever that long list was, it's applicable. You can reapply it here. But then there's a little bit different value points for SMC-D. Of course, number one is you don't require the hardware adapters. So for the customers that are using Rocky for cross-platform, we understand that. But we also understand that there's limitations to bandwidth, both the I/O technology and what you require for the NIC itself. And again, if you can take some of that off and use it internally and not use the hardware for LPAR to LPAR, that's the advantages. So you can leverage both. But SMC-D also improves your resiliency because there's no hardware to fail. So we don't have failover from adapter A to adapter B because it simply doesn't exist. So the resiliency is higher. If you have a failure, it means one of your endpoints went away. But there's nothing in between that you have to fail over to, so there are no hardware failures. So the resiliency is basically very good. The scalability, again, that's here in terms of how many users, what's my bandwidth and virtualization model. We'll talk about that in a minute, but on a System Z, you can have 8,000 users, which means virtual functions, using the technology at one time. So the scalability is very good. In terms of security, again, it's all the same security attributes we discussed with SMC-R, except we add to the fact that there's no external communication. So the bytes are not exposed to a LAN, so that's also another attribute in terms of using either HiperSockets or ISM. And then again, it preserves the value and the point of co-locating your workloads, multi-tiered workloads, etc. Again, it just upped the ante from what we had for HiperSockets, significantly improving it with SMC-D. And then usability, enablement. So how do I get this thing started? Again, with TCP/IP, you can control it with a single keyword. We're turning it on and off. And of course, I always have my disclaimer there, which means you do have to configure your HCD FIDs. We'll talk about that in a moment. But in your TCP/IP profile, you turn on one thing. You don't define FIDs in your software profile. And we just learn everything dynamically, and you can control it with that keyword. We'll talk about that in a moment. So when you list those all together, it's a pretty interesting list of value attributes. And so on to the next one then, please. And then we're just going to talk one more background topic. What is ISM? Let's talk about that a moment. So ISM is internal shared memory. It's new technology that we introduced here. You'll see on chart 22 with System Z GA2 and System Z13S. And so if you're at that level, you have the technology. There's no other pricing or add-on feature for internal shared memory. It's provided by that level of machine. But it introduces a new function that's going to be provided. It's going to be rendered to you as a virtual PCI function. So it's PCI based, and while you don't really care how we access the adapter, but you will care about how you manage it, configure it, and touch and feel it. And basically, we're going to leverage the whole ecosystem of PCI adapters by rendering it as another adapter. And so it's optimized. It provides optimized network communications for intra-CPC communications. If your ZOS is configured as a guest virtual machine, you can also use it with a VM environment. So it's either for guest to guest or guest to LPAR. There's a ZVM PTF required for the pass-through of a PCI device. And then finally, you need SMC-D support, SMC direct memory access, and that's provided with software PTS and ZOS 2.2. And so you'll see, we'll talk about that more in a moment. If you have more questions about Z13 or the announcement, there's a link there to the URL for the announcement materials about the hardware that we're describing here. In our case, we're focusing on ISM capability. Now, in the next chart, we'll talk a little bit about ISM. There's a picture here that just tries to give you the concepts, and you'll see that this is conceptually similar to HiperSockets. You can look at ISM as either a virtual adapter, or you can also view it as an internal network. And here in this example, I show logic partition 1 and 4 are connected to this adapter because they have virtual functions or function IDs. In this example, you'll see 1017 and 1018 are configured to logic partition 1 and 4. They have access, so they're eligible to use SMC-D. The other hosts are not in this example. And below, I'll show you the equivalent IOCDS statement that you can generate using HCD or directly. But you can see that you can access and communicate with each other using an ISM function through System Z technology. And then we'll talk about how the software uses that function in a moment. But this is just a quick view of the concepts of it. Again, an ISM, in this case, is a channel ID, just like IQD was defined. Sometimes, again, I'll refer to them as virtual channel IDs. In this example, it's 7EZ1, where you configure the CHID. And so it represents this internal network. It has a single network identifier. In this example, it's PNET1. So I'm going to talk about the importance of that in a moment. But notice here the entire CHID has one network ID, PNET1. So let's scroll forward. Let's talk about this a little bit more. ISM, again, here's some of the attributes. I don't know that we need to read them all, but it enables the ability for LPARs to share virtual memory. And again, that's just like RDMA. So we've basically provided our own internal RDMA, if you will. So it's basically it's an internal version of that. And so we did that with internal shared memory technology. The concepts, again, are similar to IQD. It's based on System Z's PCI architecture, so we're leveraging all that architecture and the ecosystem for configuring and managing PCI devices. We will introduce a new PCI function type, of course, ISM. It is configured using HCD and your IOCDS. Again, just like Rocky and some of your other PCI-based adapters. They support dynamic I/O, so you can dynamically add and remove ISM devices. Again, VM support is there, and it enables SMC-D. And so onto the next chart, a little bit about maximums for SMC. So what you'll see is just like IQD, you can define up to 32 CHIDs. So that would be 32 different internal networks if you wanted to configure those. Each CHID can be used by 255 users, 255 LPARs, guest virtual machines, etc. And here we call them virtual functions, but they're also FIDs, or PCI function IDs, as you know. So that's where we get our 8,000. It's 32 times 255. That's our scalability for the technology on System Z. Each CHID represents, again, a unique isolated network. So if I have a set of systems that want to use CHID 1 and another set that want to use CHID 2, I can isolate them from communicating using this technology over separate CHIDs. Virtual CHIDs for ISM support VLANs, similar to HiperSockets. The VLANs are not defined. They're inherited from your IP network. We'll talk about that in a moment. Now, the ISM technology, the architecture does define a global ID, similar to a local, link local IP address, if you will, but you don't need to configure or provision those IDs. They are dynamically done through activation. But things like MACs or virtual MACs or MTU, physical ports, frame size, all the concepts of an Ethernet fabric do not apply here. So it's basically, if I have the GID, I can find you. And we will talk about how we pass those around, but that's the only addressability we have to get into one of these devices. ISM is again supported by VM in pass-through mode using the 6.3 PTF. So on this chart here, 26, you'll see that there are really 4 topics. You know, how to use the technology is basically get your machine to the appropriate level, install the software, NHCD, define your ISM devices, and with one keyword in TCP/IP, turn it on. And so we'll talk about how to do that just a little bit. We're not going to go into great detail, but just a little bit about what that looks like. So on to the next chart. So our 4 steps. Steps 1 and 2. Your System Z needs to be upgraded to the GA2 level, which is MCL level 27, or you are at a Z13S. Both of those levels will give you the firmware and the support for ISM. And then step 2 is getting the software support. Now here this list, I don't have all the PTFs here, but primarily it's OSA CommServer, which is the PTFs listed there, along with the I/O supervisor support and the configuration support in HCD, IOSP, etc. But again, I would suggest that you use the PSP for verifying that you have the correct maintenance. But you should see a similar list in the PSP. So it's update your machine, apply the appropriate software. Okay, the next chart then. So we've covered steps 1 and 2. Step 3 is we need to define ISM. And the way we do that, again, it's treated as a PCI device. So I define a CHID, and I define function IDs, or functions and virtual functions underneath them. And depending on how many LPARs I want to access this particular CHID, or this internal network. Again, you can view it as an adapter or a unique network, each CHID that is. And for the number of users, I would define the number of function IDs that are assigned to the LPARs. And again, for PCI devices, they're considered reconfigurable. So that means that if you define a FID, only one LPAR can access it at a time, but you can configure it on and off based on your access list in HCD to allow another LPAR to use that same FID. But only one LPAR at a time can use a given FID. FIDs that are defined to the same CHID are eligible to communicate. It's that simple. So if I configure function IDs relative to the same CHID, and then those LPARs can communicate using them. Now, some examples of the SE panels to show you what you have configured are provided in the backup, so I would encourage you to look at those. I don't know that we need to examine them here, but again, it would be very helpful, I think, for you to see that in the backup. Now, HCD, you also, if you are upgrading your machine, you will need to do a change processor step. Again, that's a detail I don't show, but I did include it in the background. This is whoever manages your upgrade of your machine. This is information that's provided here for extra credit, but again, it's something that you do need to do. Because if you try to define ISM without making the step, of course, it won't be understood. HCD and IOCDS itself, I have those samples here. We're going to touch on those quickly, but I don't know how many on the phone would normally be the administrator responsible for that. but you'll see that it is a step that's required. And we're going to talk about in HCD is how you define your PNet ID, and that's an important thing where I need you to try to get your attention for just a moment if you're interested in this technology. So now on to the next chart. We're going to talk about PNet IDs for just a moment. So ISM functions must be associated with another CHID or a channel. So just like Rocky, you need to tie or associate your adapter with some IP connection, some adapter. And in the case of Rocky, it was only OSA. Now, interesting enough here, we showed you comparisons for HiperSockets and OSA. So we know that some customers use LPAR to LPAR for OSA, and some will use HiperSockets, some will use both. But basically, in this case, you can define a CHID for an ISM CHID to be associated with HiperSockets or an ISM CHID to be associated with OSD. But I need everyone to see that on bullet 2 there where it's highlighted, it's very important that if I am going to do both, that requires 2 ISM CHIDs. So they're associated by PNet IDs. So if I have a HiperSockets ISM CHID and I want to also use it for OSA, that would be separate ISM CHIDs. They cannot all have the same PNet ID. They must have separate associations. So on bullet 2 there, you'll see the association of ISM to some IP connection or adapter is based on having matching PNet IDs. So net1, net2, net1 and net1 on both adapters means we can logically bond them or associate them together. The channel devices, OSD or IQD, provide your IP connectivity. You wouldn't change any of that, your IP addresses or your definitions for those devices. But what I do need you to add is a PNet ID, just like you did for Rocky, on your OSA or HiperSocket. So if I want to associate with an ISM CHID, I would give it the same PNet ID for that ISM channel. ISM, like QD, supports a single PNet ID, so you can't have different PNet IDs. So once I design a logical network identifier, it must be the same for everything on that entire CHID. All FIDs would have that same identifier. It's viewed as having the concept of one logical port, and the PNet IDs are associated with a port. So one name for the entire CHID. And PNet IDs are not defined in software, so we tried to put it in your HCD and let all the hypervisors and operating systems discover PNet IDs. And so once you define them in HCD, you're done. And the operating systems, the OS, will discover the associated name for your hardware configuration. So on to your next chart, please. So again, ISM PNet IDs must be unique. So if I have CHID A and CHID B for ISM, they have to have unique identifiers. So again, the network ID represents an internal network, and you can't have 2 disparate or disjoint networks and call them the same thing. So they have to have unique, and that will fail if you try to configure 2 CHIDs, 2 ISMs with the same name. And they also must match a corresponding channel, IQD or OSD. Again, not both. So ISM, if I'm going to use it for both, that requires 2 ISM CHIDs with names that match HiperSockets or OSA. So normally you're using it for OSA or HiperSockets, but you can use it for both. Again, it would require 2 CHIDs. Additional PNet information illustration is provided, so I'm going to talk about this a little bit more. Again, the concepts are similar to what you saw for SMC-R, but we have several new PNet ID displays to help you understand this association in terms of, did what I configure in HCD actually match what I think I'm using? And so we've got some pretty good techniques for verifying that. So on to the next chart. So now once again, we show you this chart again. So here you'll see I have 7EZ1 is defined as my ISM virtual CHID. It has a network name of PNet1. Every FID, in this example 1017 and 1018, would be associated with 7EZ1 and PNet1. So if I have a channel that also has PNet1, I will logically bond them together. So below that you'll see again the IO-CDS statements that correspond to 1017 and 1018. The virtual functions are also defined. This is how many users are of this adapter. Again, FIDs are unique in the machine, and virtual functions the numbering start over for each adapter type. So you'll also see here that sample 1 and sample 2 are the 2 LPARs that I'm given initial access to. And on the access list, I have sample 1 and sample 2 in terms if I want to move them back and forth. And both of them, again, have PNet1 as their definition of their network, and the type is ISM. So that defines my new adapter, or my new virtual network. And then on the next chart, you'll see I have the HCD screen started here. And I'm going to walk through these fairly quickly, but you'll see that I'm adding a PCI function. This is the HCD screens that we've rendered here, and what you'll see is it has a function ID of 1017, again to match our example. It is an ISM device. I'm going to define a virtual chit as 7EZ1. That's a reserved range for both IQD and ISM. And I'll start with 1 for virtual functions, and I'll just have a description of it there in terms of what processor this is associated with. Now I'll hit enter on that, so now I have 1017 defined. And when I hit enter, I go to the next screen, and the next screen will ask me for a PNET ID. So for ISM devices, it is PNET 1 in this example. Now some of the adapters will allow more than 1, but we've said already that ISM only supports 1. So for every FID you define, I believe HCD will populate the screen for you, so you should never change it. It should be 1. So 1 PNET ID and the same name for every FID for the same chit. For, in this case, 7EZ1, they would all have PNET 1. And so scrolling to the next screen, then I would also assign some partitions to have access to 1017. In this example here, I'm going to give it access to LPAR sample 1, and then I would hit enter, and now sample 1 would have it configurable for that partition. I can now, in that LPAR, I can now configure on device 1017. So if you scroll forward, you'll see that I also added, just as an example, as an IQD device. Again, you should all be familiar with defining CHIDs in devices for IQD, but the only reason I showed this in here is the point of associating it. So here I'm defining IQD as a device. I've given some device numbers. So I'm adding. This is an add channel path step, and if I go to the next step, what you'll see here, this CHID is 7EZ0, and then onto the next chart, you'll see that it's going to ask me now for PNET ID. So if I make it PNET 1, I've just logically associated this IQD channel to my ISM channel. So 7EZ1 and 7EZ0 are now logically associated in the sense that they have the same PNET ID. So software can now logically tie the two together. And so onto the next chart, you'll see here, this again, I'm defining my access list. So what LPARs do I want to have access to this IQD channel, and what devices I would define. So this is existing steps again. So you'll see that that's you can hit enter and provide that channel path access list. And then on the next chart, you'll see that we'll talk a little bit about a summary of ISM. So now we just defined an ISM device and paired it up with a HiperSockets device and HCD, made it available to these two LPARs. And now finally we get to the CommServer part. So what do we do in CommServer to turn the function on? And this is where we like to talk about that it is in fact one parameter. Similar to SMC-R on the global config, we have a parameter now called SMC-D, and it defaults of course to off, but when you're ready to test or use SMC-D, that single keyword will get you going. Unlike Rocky, you do not define FIDs or ports or MTUs because they don't apply. And the FIDs that we did define in HCD will just dynamically discover. So as soon as you've configured that on to the COSL part, in this case 1017, and TCP/IP is started with this parameter on, we will just discover 1017 and activate that ISM device. And then what we will do is we'll also look to bond or associate that ISM device with something that has the same PNET ID. In this example, PNET 1 will discover IQD channels have PNET 1, so they are now TCP/IP connections over that channel are now eligible for SMC-D using this ISM fabric. And so again, the OS can be enabled for both SMC-R and SMC-D. You can control it on the global config. You can toggle them on and off. You can also change it at more granular level on the interface statements, just like you could for SMC-R. Now, so if both peers, both ZOS instances are on the same footprint and they're enabled for SMC-D and they have access to the same vCHID, then they have connectivity. If you also use VLANs, you have to be on the same VLANs. Where do my VLANs come from? We'll talk about that in a moment, but basically they're just inherited from your IP network. So if you have them on IP, we'll partition your work on your ISM fabric as well. Again, Your ISM FIDs must be associated with an IP network. That's done through PNet IDs. Your OSA or IQ channel must have a matching one. And again, OSA and HiperSockets cannot both be associated with the same ISM chit. Host virtual memory. Do I do anything different, special? Where does it come from? And the answer is no, you do nothing different. It's similar again to SMC-R. The OS manages your memory, exposes it to the adapter just like it did for RDMA, and then it's logically shared by the peer host using something like an RDMA technology. But in this case, we leverage our existing PCI I/O translation architecture. So that is all existing logic that we use for other PCI devices. It's also used by ISM devices. So it's your virtual memory that's managed by z/OS and CommServer. So it's not special memory. ISM is not like a coupling facility. It's just accessing virtual memory within the OS itself, just like SMC-R. So on to the next chart. And now, so here's the one keyword that I promised, and it's SMC-D. If you turn it on, you get the function. There are some optional keywords here if you want to tune SMC-D. Most users will never need to touch those, but they're the same tuning parameters that we provided for SMC-R. You can limit how much fixed memory is used for the function with that keyword. You can also adjust, keep alive on your IP fabric. Remember, your TCP/IP connection stays active, and if you need to keep alive over that fabric, you can control it with these parameters here. But normally, for most users, that default is fine. And certainly for a test environment, most often you would just enable the function, and you're off and running. Okay, so we've gone through HCD. We've looked at the TCP/IP configuration, and then finally we'll look at how we rendezvous. Now, we touched on this same chart when we reviewed SMC-R, so let's review it again. How does this happen for SMC-D? It's basically identical. Now, in this first example, it's a HiperSockets network, so the network is inside the machine. So now the green cloud is inside the machine. It is an IQD fabric, and in this example, it's PNet1, and my ISM device is also PNet1. And I show an ISM and a HiperSockets device side by side. How did they get there? They're associated because they had the same PNet ID, and we logically bond them together, treat them as having access to the same physical fabric, and in this case it's a logical fabric. And what we do here is we show the old technology in green and the new technology in yellow. And again, you connect over TCP/IP. In this case, the fabric is IQD over your HiperSockets device. And if we're both enabled for SMC, we'll exchange our credentials, and we'll discover, we're both enabled for SMC-D, and we're also on the same physical machine. The architecture can do this, and if it does that, it will switch out dynamically. Instead of using SMC-R, it will use SMC-D, and it will keep the IP connection active, but will dynamically negotiate, switch, and now data is exchanged using the SMC-D protocol, which uses the ISM fabric. So that uses PCI store block, as I show in this instruction, to write data from one L part to the other using the exposed memory. And ISM, again, acts a little bit like RDMA in the sense that instead of remote direct memory access, it's direct in the sense that it can access the memory on the same physical machine. So that's the dynamic transition from TCP/IP to SMC-D. It's virtually identical to SMC-R. This shows on a system C13. Now, again, those two networks, those two channels were associated because they had the same PNet ID. Now, if you look at the next chart, you'll see the same example for an OSA network. Now the network is outside of the Z13. It's an external LAN. And instead of using a HiperSockets NIC, we're using an OSA NIC. We're using TCP/IP to connect. Once again, we'll negotiate, and we'll find out, we're using an Ethernet network. We're both enabled for SMC-D, and it turns out we're still on the same machine. So we could, again, switch out to use SMC-D using the ISM fabric. In this case, the CHID has the same network ID as the OSA adapter, so we logically put them side by side. You can view them as one adapter, but they are now logically bonded or associated because they have the same identifier. And then, again, we'll switch out and exchange our credentials and use SMC-D. Now, the data transfer occurs using the SMC-D protocol, and it bypasses the TCP/IP processing in the data path. If the TCP connection breaks for any reason, we will break the SMC connection. Again, that architecture is just like SMC-R, and so you'll see here that we've leveraged all of that protocol, but now inside the machine. So here you've seen that a little bit different from Rocky. You can use HiperSockets network or an Ethernet network, but again, whatever you're using for access, you're eligible for either case to use ISM. Your ISM device that's associated with OSA would not be the same ISM CHID that's associated with HiperSockets. That needs to be a separate CHID if you're going to do both. Now, again, so over onto the next chart. And you'll see here, this is the picture that I'll make a note to you that is all the way back on chart 12 when I showed you how you use them together. So this is a chart trying to show how you use Rocky and SMC-D together. And this time it focuses on a little bit about the network, the device association, and what the IP topology looks like. So now the green cloud is actually Ethernet, but on the machine on the left, once again, they're on the same footprint. And whereas the machine on the right is a separate physical footprint, so when we rendezvous with system B and C, they'll discover, hey, we're enabled for SMC, but we're different machines, we'll use Rocky. Whereas when systems A and B rendezvous, they'll look at, hey, we're enabled for SMC, we're on the same footprint, we both have access to the same ISM network, so we'll use SMC-D. And so you can see how both technologies can be leveraged simultaneously, and the protocol determines which form of SMC to use based on physical proximity. And so, again, I would encourage you to flip back and forth from chart 12 and this chart 42 to look at the two different perspectives and see how this works. In this example, Rocky, ISM, and OSA all have the same network ID. Certainly on the Z13 on the left, they all have the same name, all three types of adapters, PNet1, whereas on the right, that system just has PNet1 for Rocky and OSA. But I'm not using HiperSockets in this chart. If I were to use HiperSockets, it would be a different PNet ID, PNet2, for example, and it would be a different ISM CHID. But here you can see how you can just combine ISM with Ethernet. So hopefully that all makes sense, and you can use both protocols together. And then on to the next chart, we will just look at one reminder. So for SMC-R to be eligible, you have to have access to the same IP subnet. We can't route Rocky frames, at least not at this point in time. So one of the key rules is your two operating systems must have access to the same IP subnet. In this example, I'm showing IP subnet A and B, and they talk through an IP router. For TCP connections that take this path, they would not be eligible for SMC-R. And we made the rules the same for SMC-D in terms of preserving whatever reason you put that router between these instances. We're declaring that today SMC is not routable, period. SMC-R or SMC-D. So in order to be eligible, both instances must have access to the same IP subnet. So if they both had access to A, this would work, but A and B in this picture, that TCP connection would not work in this example. So that still carries over for SMC-D as well. And then the next chart, please. And so just a quick few words about VLAN. So again, you can take an ISM network here shown on chart 45, and you can give all the LPARs access to this with no separation at all. In this example, this is what we've been looking at. But if you look at the next chart, if you happen to have two VLANs defined, so what we can do is you can isolate your traffic or your systems by VLANs, and so the technology ISM also supports VLAN support as well. The VLAN definitions are inherited from either your OSA or your HiperSockets. Whatever you're using for IP connectivity, we just adhere to the same VLAN rules, and we will separate your traffic on the same CHID using the VLANs from your IP connectivity. So basically you can isolate your traffic using VLANs on the same CHID, or if you go to the next chart, you'll see an example. I have two CHIDs used for ISM, and you could separate your production and test machines using different CHIDs, or you can also separate them using VLANs. In this example, I've done both. So I've shown you that you can use different CHIDs and you can separate on VLANs. And a couple of points here is that each of these LPARs have a single ISM FID, with the exception of LPAR N here. It actually has two ISM devices because it's accessing, I need an ISM FID per CHID that I'm accessing. So when I'm accessing CHID A, I have ISM device 1, and then for CHID B, I'm accessing it via an ISM device, another unique FID. Well, if you contrast that with LPAR 5, it has two VLANs onto the same CHID. So I only need one FID there, and I could have a dozen VLANs. I don't add functions or virtual functions for each VLAN. So they all can be accessed through the same function ID. I only need another FID if I'm going to a completely different fabric. So this is an example of how you can isolate your workloads, and it's all done dynamically. You don't define VLANs or FIDs. We discover them and just mimic your IP connectivity. So on to your next chart, please. And then finally, how do I verify this? So if you just scroll forward, you'll see that if I'm using PCI devices, and I can start by using my ZOS D-Space PCI. So there you'll see in this example that display shows there's my CHID 7EZ1, and I have two devices that are in the allocate state, and that state means that some operating system is actually using those two devices, and in this example FIDs 600 and 601 are being used by this job name. So again, DSpace PCI will show you what you're using for PCI devices, and so that's been enhanced for ISM. And on to the next chart, here's a very important display. Now you can display your PNet IDs for both channel devices and PCI devices. So once you know your actual channel number or your FID number, you can issue a more detailed display in iOS that will give you back more detailed information about the channel path. The top example is OSA, and the bottom one is HiperSockets. But you see we've enhanced that display to also return your PNet ID. This is important because we can't display PNet ID until we use the device. In some cases, if you have configuration errors, it's nice to be able to display this. Well, I bring this display up and it shows no PNet ID. And you walk down the hall and talk to the guy that's supposed to do your HDD definitions, find out where's my PNet ID. And so, if it's the wrong PNet ID, you can also have a talk with him about that as well. Now, if you go to the next chart, I have the same example for PCI devices. You'll see again. And here's a set of netstat displays, and the blue fonts, hopefully you can see that, are highlighting the differences. In this first example, we are showing SMC-D enabled IQD interface. So you can see that I'm doing a netstat dev links with an interface name of HiperSockets, IQD1. And our display has been enhanced to say that this IQD chip, it has a PNet P2, and it's also associated with SMC-D, so I must have found an ISM adapter that also had P2, and down at the bottom it shows you the interface that's associated with that ISM adapter. So same display, enhanced for ISM. If you scroll to the next one, it's a display that allows you to do a dev links for OSA. Again, a similar display. And what you see here is this OSA is enabled for both Rocky, SMC-R, and SMC Direct, and they're all configured to use P1. And it also gives you the associated logical interfaces into both Rocky, the RNIC, and to ISM, described below, highlighted in blue. So you can see that this IP traffic over this OSA is eligible to use both forms of SMC. If you scroll to the next one, you can use a dev links that shows PNet ID. So this is a new display, very handy. So if I say PNet splat, I'll get all my PNet IDs. In this example, you'll see I have PNet 2. I have two HiperSockets interfaces with an ISM interface. So I got an IPv6 and IPv4 HiperSockets interface that are now associated with ISM. And on network ID P1, you can see there I have a V6 and V4 OSA that's associated with an ISM device and an RNIC as well. So that's a very handy display to show. When we get done grouping these devices, you can use this display to look at a specific PNet or all your PNets as based on devices defined. So that's very handy for confirming what's associated. Again, that's only valid after the interfaces are active. If you can't get them active, use the iOS display that we showed you initially. And then on the next chart, there's a display of PNet ID again, and this one is a specific display. When in this example, it's P2, and what you'll see here is that we'll give you a little bit more detail on the specific devices using this network ID. In this example, again, it's HiperSockets connected to this ISM interface. It shows you now we get into VCHIDs and PFIDs and the individual subchannel devices used here. So a little bit more detail when you use a specific PNet ID. Again, this is new. And then on to the next chart, you'll see we have, you can display the specific connection. That's that all. In this example, I'm looking at ports 31 and 32. You'll see that connection is shown here. and you want to know, okay, I've started up my workload, is it or is it not using SMC, and which form of SMC? And so you'll see that it's been enhanced, that below it gives you SMC-D status. So the SMC information will either come out as SMC-R or SMC-D or none. In this example, you can confirm that this workload for this specific TCP connection is in fact using SMC-D. And you can see a little bit about the characteristics of that logical connection over ISM. So here's a way of confirming your workloads are actually using the new protocol. And then on to the next chart. You'll see here's a DevLinks SMC, and this gives you all of your interfaces that are SMC oriented. And here we give you an interface up the top, EZA ISM-01, which is a name we dynamically define, but it just shows all of ISM and RNIC interfaces. In this example, we have an ISM interface along with the SMC-D logical link information. That's how we connect to another peer, kind of like the link information that we have for SMC-R. We also have a logical relationship with a peer, so you can see who you're connected to. So that's another interesting display that helps for ISM manageability. Again, you see the PNet ID and the devices that are being used. And then on the next display, next page, you just basically is a summary of how you verify. Again, it requires 2 instances of ZOS on the same Z system, and then there's a list of requirements for those ZOS instances having access to ISM and their FIDs configured on to the LPARs. Please don't forget that step. They have to have them configured on. You have to have direct access to the same IP subnet. That's true for both Rocky and for ISM. You can flip it for ISM. It could be either via OSA or HiperSockets for IP connectivity. And then if you define an IP interface with the same VLAN IDs, so if you do use VLANs, of course both hosts have to have access to the same virtual network. And then you enable both ISM and SMC-D and verify its status using netstat we just talked about. And then finally start your workloads and verify the connections are actually using SMC. And then optionally you can drill down on your performance if you have a performance team that can evaluate and do a comparison of either HiperSockets or OSA compared to SMC. And hopefully if you get that information, we'd love to talk to you about what you're seeing. And then finally, I think on the next chart, so it's just a couple statements about SMC-AT. Again, it's hopefully most of you are familiar with the tool, but it requires no special hardware, and it's just PTS that we shipped all the way back to 1.13. It allows you just to evaluate and measure your TCP/IP traffic, and it basically provides a report in 2 sections. One is all the connectivity that's already on the same subnet, which is called direct attach, and it provides all the other connectivity that would be eligible for SMC, but they were not necessarily direct attached. And then you can see, okay, today what do I have, and what's my opportunity to move things around if I want to optimize my exploitation of the technologies either for remote or direct. And so that tool is usable today. And if you scroll to the next chart, this just gives you a little bit more information about the tool, what it produces. Hopefully you've seen it. If not, I would encourage you to go to our website. Again, it's listed here. We have more information. There are the PTS listed to get the support. Again, it's just measuring your existing TCP/IP traffic, puts it into a nice summary to show you what's your opportunity for usage of SMC. No special tooling or hardware or any configuration changes. It just measures what you ask us to sample in terms of your peer networks, either IP addresses or subnets. So that was there's the SMC references, and again, that's what's out on that website. Again, there's performance information. The SMC-D information is being added now, but you have the overview. There's an FAQ out there that will be out there, and it's also available on other IBM websites today. I would encourage you to look at that if you think you have questions. We hopefully believe that frequently asked question document will answer every question you have, and if it doesn't, we'll add that question to that document. But between this overview chart deck and that FAQ document, it should tell you everything you need to get you going. And if you have questions, my contact information is on the front of the charts. Feel free to send me an email or reach out to me, and I'll be glad to work with you and answer your questions about SMC in general, SMC-D that we're introducing, along with ISM.